Theory that could finally explain black holes. Black holes are among the most mysterious objects in the cosmos, and they appear to be draining away the very fabric of space and time in a manner similar to water pouring down a drain. But what are they specifically? Are they more widespread than we realise? Do they warrant our concern? What function do they serve in the cosmos? There are only a few of the big picture issues that some of the top astrophysical brains have been debating for many years. Let's see what, if anything, they have discovered about the universe's great devourers. In this video, we will learn about the theories that can finally explain black holes. So be ready for a trip in a spaceship to the domain of black holes. Black holes are a point in space that are so dense that they form massive gravity wells. After a certain point, even light cannot escape the tremendous gravitational pull of a black hole, and anything that gets too close will be stretched and crushed like putty in a process known as spaghettification, regardless of whether it's a star, planet or starship. Black holes are classified into 4 types: stellar, intermediate, supermassive and tiny. The most well-known mechanism for a black hole to develop is through star death. Most stars will expand, lose mass and cool to form white dwarfs as they near the end of their lives. However, the most massive of these flaming things, those at least 10 to 20 times the mass of our Sun, are doomed to become either super dense neutron stars or stellar mass black holes. Tremendous stars explode in massive explosions known as supernova in the terminal stages. A burst like this flings star stuff into space while leaving the luminous core behind. Nuclear fusion provided a continual outward push that countered the inward pull of gravity from the star's own mass while it was alive. However, in the stellar remnants of a supernova, there are no longer any forces to defy gravity, and the star core begins to collapse in on itself. A black hole is formed when its mass collapses to an infinitely small point. All of that stuff, many times the mass of our own Sun, packed into such a small space, gives black holes their tremendous gravitational pull. There could be thousands of these stellar mass black holes in our own Milky Way galaxy. Supermassive black holes can have masses comparable to billions of suns. These cosmic monsters are most likely to be found at the centres of most galaxies. Sagittarius A, the Milky Way's supermassive black hole, is more than 4 million times as big as our Sun. So far, the smallest members of the black hole family are theoretical. These little vortexes of darkness may have come to existence just after the universe started with the Big Bang 13.7 billion years ago, and then quickly vanished. Astronomers also believe that a type of phenomenon known as intermediate mass black holes exist in the cosmos, though evidence for their existence is still debated. Black holes can grow in size throughout their existence, sucking gas and dust from anyone that gets too close.
While you're getting stretched, you're getting squeezed, extruded through the fabric of space like toothpaste through a tube.
Astrophysicist Neil deGrasse Tyson famously said. But contrary to popular belief, black holes aren't cosmic vacuum cleaners. To lose this gravitational tug of war, objects must get fairly near to one another. For example, if our Sun were to be suddenly replaced by a black hole of comparable mass, our planetary family would continue to circle unaffected, albeit much less warm and lit. Looking through the shadows. Because black holes absorb all light, astronomers can't see them like the countless glittering cosmic objects in the sky. However, there are a few indicators that indicate the presence of a black hole. For starters, the immense gravity of a black hole pulls on any nearby things. Astronomers utilise these erratic movements to infer the presence of an invisible monster lurking nearby. Alternatively, objects can orbit a black hole, and astronomers might hunt for stars that appear to orbit nothing to identify a likely candidate. That's how astronomers identified Sagittarius A as a black hole in the early 2000s. Black holes are notoriously messy eaters, which often reveals their position. Their tremendous gravitational and magnetic forces superheat the infalling gas and dust, causing it to radiate radiation. Some of this blazing matter surrounds the black hole in a swirling region known as an accretion disk. Even matter that begins to sink into a black hole is not always there to stay. Infalling stardust can sometimes be ejected by black holes in massive radiation-laden burps. So, to your surprise, all of the representations of black holes that you've seen on the internet are merely assumptions. But don't expect humans to give up so simply. The Event Horizon Telescope (EHT) team published the first photograph of a black hole in 2019. While the telescope was studying the event, the EHT noticed a black hole in the centre of galaxy M87. It appeared to be a large black circle surrounded by a ring of flames. The black hole is 6.5 billion times more massive than the Sun. This was the first direct visible evidence of a supermassive black hole and its shadow. There is still so much to discover. General Theory of Relativity by Albert Einstein. Black holes are extreme manifestations of Albert Einstein's general theory of relativity. Scientists believe that at the heart of each black hole is an indefinitely small and dense point known as a singularity. Gravity is so intense near the singularity that it creates an event horizon around it, where gravity's pull exceeds even the speed of light. The event horizon of a black hole is its furthest edge. This is the point of which gravity exceeds light's capacity to escape the black hole's gravitational attraction. To escape the event horizon, you would have to travel faster than the speed of light. It is the actual point of no return. Once you cross through it, there is no way out. That was, at least, the conventional wisdom. Physics laws fail down at infinitely small singularities. That's when two seemingly contradictory branches of physics, quantum mechanics, which describes the ultra-small, and general relativity, which describes the extremely massive, collide. Researchers want to unite the two sciences by investigating the nature of black holes. What's the problem? Because matter is incapable of compressing into an indefinitely small point. The singularity appears to be physically impossible. Hawking's information paradox. A seemingly insoluble black hole dilemma, initially suggested by physicist Stephen Hawking, may be overcome through wormholes traversing space-time. The black hole information paradox relates to the fact that information cannot be destroyed in the universe. Yet, when a black hole eventually evaporates, any information it ate should have long since perished. Let us only keep our hopes up for the future. What are your thoughts on these all-consuming invisible creatures lurking in space, and what is beyond?